In the last lecture, we have seen how to find out different currents and voltages of a compound generator when it is designed and adjusted for a particular terminal characteristics. It will be also interesting to find out how many series turns we will need in order to get that kind of a characteristics. Let us try to solve a problem like that. For that, let us assume we have again a long shunt cumulative DC generator with the following rating 3.3 kilowatt, 110 volts, 4 pole, 1500 RPM. The OCC of this generator is given by the following table. The shunt field current and the induced voltage. The residual voltage is 5 volts for 0. This is in amperes and this is in volts. 0.25, 40, 0.5, 65, 0.75, 82.5, 1.0, 95 volts, 1.25 amperes, 103.5 volts, 1.5 amperes, 110 volts, 1.75 amperes, 113.5 volts, 2.0, 17.5 and 2.3 amperes gives you 120 volts on no load for this machine. Further, the following data is given. Armature resistance equal to 0.20 ohm. The total brush contact drop on two brushes equal to 1 volt. The shunt field resistance RSH equal to 73.33 ohm. The number of shunt field turn in SH equal to 200. The series field resistance equal to 15 ohm. The effective armature reaction field current, that is ISH armature reaction, is proportional to armature current and is given by 1.5 times IA. So, if we want, let us say at n equal to 1500, we want the terminal voltage at no load should be equal to terminal voltage at full load equal to rated terminal voltage, that is 110 volts. So, we want a flat compounding characteristics. The question is, what should be the number of series field turns? Let us see how to solve this problem. For that, we see that at rated load is equal to 3.3 kilowatt, Vt at full load equal to 110 volts, therefore, IL at full load equal to 3300 divided by 110, this is equal to 30 amperes. So, ISH at full load, since this is a long shunt connection, ISH is Vt at full load, long shunt connection, shunt field is connected across the load terminal, divided by RSH, this comes to 1.5 ampere. Similarly, ISH at no load is also Vt at no load, which is again 110 volts. This is also equal to 1.5 amperes. So, at full load, what is the armature current? IA at full load equal to IL at full load plus ISH at full load, this is equal to 30 ampere plus 1.5 equal to 31.5 ampere. So, what is the induced voltage EB, E at full load? This is equal to terminal voltage at full load plus IA full load, and this is a long shunt connection, therefore, this should be equal to RA plus RAC plus the brush contact drop. This is equal to 110 plus 31.5 into 0.2 plus 0.15 plus 1, this comes to 122 volts. The OCC data is given here, from which we can plot the OCC of this . The OCC data gives for a maximum it gives up to 2.3 amperes and the corresponding voltage is 120 volts. However, we find that here the induced voltage will be 122 volts. So, it should be somewhat out of this range and you will have to extend the OCC. However, if you do the exercise then you can find out the required field current comes out to be, so ISH from OCC for E equal to 122 volts, this comes to is 2.375 amperes. Now, it is mentioned that the so in order to generate a induced voltage of 122 volt for this compound generator, the ISH effective should be ISH effective should be 2.375 amperes, but for long shunt connection we know ISH effective equal to ISH plus NAC by NSH into IA minus ISH armature reaction. Now, we know ISH equal to 1.5 amperes, NSH equal to 200, and also we know ISH for armature reaction, the effective armature reaction and field current equal to 1.5 IA. At full load IA equal to 31.5 amperes. So, ISH due to armature reaction at full load equal to 1.5 by 200 IA by 200, that is the shunt field current. Zero 0.236 amperes, and we know that ISH effective is, so we have 2.375 amperes equal to 1.5 ampere plus NAC by NSH is 200 into 31.5 minus 0.236 ampere. Solving this, we get NSE approximately equal to 7 turns. Now, this will give a flat compounding characteristics at a rotational speed of 1500 rpm. It will be interesting to see how the characteristics will change if the rotational speed, let us say, increases from n equal to 1500 to n equal to 1600. Let us first see what will happen to the no load voltage. At no load, with the connection, we know that at no load IF equal to ISH equal to 1.5 amperes and the terminal voltage VT equal to 110 volts. So, let us find out what will happen at 1600 rpm. For that, let us draw the OCC at 1500 rpm. And so this is the 1.5 ampere and the corresponding voltage is 110 volts. We can, of course, so this is the field load line. We can, of course, draw the this is at n equal to 1500 rpm. We can similarly draw the OCC at 1600 rpm and find out the intersection point from that curve. But as we will find that there is no need to draw this OCC. In fact, the field current can be very easily computed by finding out this point P. What should be this point P? Let us say this IF1 is equal to some current ISH1. So, from the and let this be E1. So, E1 equal to the magnetizing function characteristics F into of ISH1 at 1500 rpm. So, at 1600 rpm this is also equal to RSH ISH1. At 1600 rpm this will become 16 by 15 times E1 So, at 1600 rpm the OCC will be given by 16 by 15 into F of ISH. So, let us say it will intersect at a this intersection point is given by ISH2 and the corresponding voltage is E2. So, E2 equal to this is E2, E2 equal to 16 by 15 F of ISH2 2, this should be equal to RSH into ISH2. Hence, the intersection, the current ISH can be found out from f of ISH2 equal to 15 by 16 times RSH into ISH2. That is, if this is with a slope of RSH, we simply draw a new field load line with a slope of 15 by 16 RSH, and wherever it intersects with the OCC at 1500 rpm will give the value of ISH2. Following this procedure, we find that ISH2 will be for this case will be 1.62 amperes, and the corresponding voltage E2 dash, that is this voltage E2 dash will be equal to 111.28 volt. So, at 1600, so E2, that is the no load terminal voltage at 1600 rpm will be 1.28 into 16 by 15, that is 0.7 volts. Now, if we want the same 110 volt at 1600 rpm, how many series turns we will need? So, on full load Vt equal to, we want to be same 110 volts, then the ISH will be equal to 1.5 amperes, and IA will again be IL plus ISH equal to 31.5 amperes, and E will again be equal to 110 plus IA into IL plus ISH plus EB, this will again be 122 volts. Now, in the same manner as we found out from the, for the no load condition, we know that in order to generate this voltage, ISH at 1600 rpm will be the effective ISH at 1600 rpm should be 1.78 amperes. We know ISH AR at full load equal to 0.236 ampere. Therefore, effective ISH 1.78 should be equal to actual ISH plus NAC by 200 IA plus ISH AR, which gives that the, if we now need to keep it at 110 volts, required NAC will be just 3. So, the operating speed has a very prominent effect on the output characteristics of a compound generator. However, by adjusting the number of shunt field turns we can get the desired characteristics. Now, we have seen that any electrical equipment has a particular output rating. The same is true for DC generators. It is designed to supply certain load. Now, if the load increases, then what do I do? In which case, one approach is to interconnect different DC generators as shown. Suppose we already had a DC generator, a shunt generator, let us say, which was supplying a load of I L. If I L is less than the rated current of this DC generator, then only this generator will be able to supply this. But if there is a possibility that this I L can be larger than the connected generator, then it will be imperative to bring in another generator and connect them in parallel. For that, initially this generator will first be run at no load. Again we are assuming this is another shunt generator. Before this generator is connected, it must be ensured that the terminal voltage let us say it was supplying current of I L at a terminal voltage of V t. It must be made sure that the incoming generator at no load generates a terminal voltage of V t. Then this switch can be closed, and once the switch is closed, then these two generators are connected in parallel. However, that does not ensure that the second generator shares any load. In fact, if the no load voltage of the incoming generator has been adjusted to match the terminal voltage of the existing generator, when it is just connected, the second generator will not share any load current. That can be seen from the output characteristics of these two generators. Let us say this is a shunt generator. So, initially this was the output characteristics of this generator. It was supplying this is the load current of the first generator, this is the load current of the second generator. Let us say this was the terminal voltage and it was supplying the full current I L. Now, for the second generator we have adjusted and the terminal voltage was V t, this was V t. We have adjusted the no load voltage of the second generator to be V t. So, this is the characteristics of the second generator. Now, of course, during this period the second generator load current is 0, the first generator load current I L 1 is the total load current I L. Now, if I want to transfer some of the load current to the second generator, this is generator 1 and this is generator 2. Its field excitation has to be increased, so that the output characteristics moves upward. Let us say by some increase we bring the second generator characteristics as per the dotted line. If the load remains constant, then what will happen? Total load current will remain constant. So, some load will be shared by the second generator, so that the total load current still remains. Now, this will be the load shared by the second generator and this will be the load shared by the first generator. However, we see that if we do this, then there is a increase in the terminal voltage. If we want to bring the terminal voltage back to the original level, then the field excitation of the first generator must now be reduced. So that now this becomes, this will, once the field excitation of the first generator is reduced, then its output characteristics will move down. This will reduce the load shared by the first generator and that load will be transferred to the second generator. Thus, for interconnected DC shunt generators, it is possible to change the load shared by these generators by controlling their field excitation. However, the situation is somewhat more complicated if a compound generator is used instead. Let us see the situation with a compound generator. This is the DC bus to which these two generators are connected. So, these are, let us say, short shunt generators. This is generator 1, this is series field 1. Similarly, there is a second generator, with its own this is the shunt field 1, this is shunt field 2, this is series field 2. Now, let us see what will happen. Suppose these two generators were sharing the total load current I L in some manner. Suddenly, suppose for some reason the field excitation of this generator increases, then what will happen? The terminal voltage of this generator will move up, hence the share of the load current of this generator will increase. As the share increases, the series field excitation also increases. As the series field excitation increases, the induced voltage increases, hence this further increases the load current of this generator. This is a positive feedback mechanism, particularly if it is a over compounded generator, in which case then even a small change in the field excitation of one of the generators will create a very large disturbance or inequality in the sharing current sharing pattern of the parallel connected generators. Therefore, if we want to use compound generators in parallel, simply this connection is not good enough. We have to make a special connection called a equalizer bar. So, in effect what we are doing, we are connecting the machines not only parallel at the terminal, but also parallel at the armature point. So, if we do this, then the armature of the two generators are in parallel, the series field of the two generators in parallel. So, any increase in the armature current of one of the generators is shared by both the series fields, and in fact this sharing can be controlled by connecting additional resistances across one of the generators. This is R1, this is R2, and suitably designing them and thus preventing this positive feedback mechanism. It is possible to find out, to calculate the values of these resistances, and we will explain this with the help of a example. Let us say we have two over compounded short shunt generators connected in this manner with the following data. the rated bus voltage V t equal to 220 volts for generator 1. RSH 1 equal to 82.0 ohm, RAC 1 equal to 0.15 ohm, IL 1 at full load, IL 1 rated equal to 100 amperes, and from load characteristics we know for V t at 100 ampere, V t full load for this machine is 220 volts. Similarly, for the second machine, generator 2, RSH 2 equal to 61.5 ohm, RAC 2 equal to 0.07 ohm, IL 2 rated equal to 150 amperes, and from the load characteristics we know V t IL 2 at 110 amperes of load current, the V t is 220 volts, and at 150 amperes of rated current, this 225 volt, that is this generator is over compounded. We want both the generators to operate at their rated load current, that is we want IL 1 to be equal to 100 amperes and IL 2 to be equal to 150 ampere. So, what should be the values of I SH 1, I SH 2, and what should be the value of R 1 and R 2, where this is how R 1 and R 2, this is called a diverter resistance, this is called a series resistance. R 1 equal to how much, R 2 equal to how much. We are supposed to find this out. For this, we note that both the machines are supplying their rated current. This voltage is 220 volt. This is positive, so this is giving a current of 100 ampere, which is its rated current. Similarly, this is giving a current of 150 ampere. Note that the current, this is 150 ampere, but the series field current ISC 2 is not 150 ampere, while ISC 1 is, this is 100 amperes. This current flowing through ISC 2 can be adjusted by controlling the diverter resistance R 2. Since IL 1 is equal to 100 ampere, and the induced voltage E 1 should be equal to terminal voltage 220 volts plus this is short shunt connection. So, this is the shunt field resistance into load current 100, this comes to 235 volts. Hence, this is short shunt connection. So, ISH1 should be equal to 235 divided by the RSH1, which is 82, this comes to 2.86 amperes. Now, this voltage is E1, this is E1. Now, because of this equalizer connection, see this end is connected here and this end is connected here. So, E1 must be equal to E2. So, because of the equalizer connection, E2 equal to E1 equal to 235 volts, and the shunt field of the second machine is also, it is a short shunt. So, connected across E2. So, ISH2 this should be equal to 3.82 amperes. Now, let us see, we have from the load data we have seen when the machine 1 supplies 100 ampere of load current, its terminal voltage is 220 volt, which is same as the bus voltage. However, for the machine 2, the data shows that when IL2 is, when Vt is 220 volts, then IL2 is 110 amperes. So, if 110 amperes flows, then if IL2 is 110 amperes, then Vt equal to 220 volts. The armature terminal voltage, if IL2 is to be 110 ampere, then in which case E2 becomes 220 plus at a terminal voltage of 220, IL2 is 110 volt amperes. So, this will become 220 plus 0.07 into 110 equal to 227.7 volts. But since these are parallel connected, E2 must be equal to 235 volts. So, the additional voltage of, so this voltage of 235 minus 227.7 volts, this additional voltage must be dropped across this resistance R1. So, R1 should be equal to this divided by 110 amperes, because the series field winding current must be equal to 110 ampere, so as to generate 220 volt of 220 volt across the 220 volt terminal voltage from machine 2. So, this gives the value of R1. So, this R1 comes to 0.0664 ohm. Then what should be R2? If the current through the series field is 110 amperes, therefore, the current through, since the total current is 150 ampere, this is 40 ampere. So, 40 into R2, these are connected in parallel, equal to 110 into 0.0664 plus the shunt field to resistance, which is 0.07 ohm. So, from here we get R2 to be equal to 0.375 ohms. So, we see by this method we can find out what should be the value of R1 and R2. Thank you.